All right, we're going to be looking at some rotational stuff over the next 2 units. And rotational is a good review unit because basically everything that we've done with linear quantities, now we will do with angular quantities. And so it'll be a reminder of what we did in kinematics and force and energy and momentum as we go through these rotational things. So as we do that, we're going to develop this table of analogs. Every one of our linear variables will have an angular equivalent. A position or displacement relates to an angular position, velocity, angular acceleration, and they're also rotational equivalents of mass, force, and momentum. A linear position, of course, is related to an angular position, which would be a theta. As you know, arc length, the formula for that is S equals R theta, and this is, and S is a distance, right? It's a distance along an arc. So for an object traveling in a circle, or a point on a rotating object, the distance that point travels is equal to the radius times the angular distance that it travels. If we take a time derivative of a distance gets us a velocity, and the time derivative of an angular displacement is an angular velocity, for which we use the Greek letter omega, which is kind of a curvy W thing. So angular velocity is omega. And if we take one more derivative, we get an acceleration. And then we're taking the time derivative of angular velocity, which is angular acceleration. And each of these is, doesn't say it here, but it is tangential. This is the tangential component of velocity, the tangential component of acceleration for an object that is rotating or revolving. And because everything is just r times, or everything is just different from the linear variable by a factor of r, if we plug all that into our equations of kinematics, we get the same equations, just with the rotational variables. So we can use the average velocity equation. I forget whose equation we call this. Is it Pratik's, maybe? Whatever. There's that one. We've got the time-dependent equation, the time-independent equation, and of course the definition of acceleration. And the direction of all these quantities is determined by the right-hand rule. It might be hard to see on this video. I'll talk about it. I'll go over it in class again, just in case it is hard to see. So an object is rotating, and let's say it's rotating counterclockwise. It's going around this way. Well, the direction of that angular velocity, we just curl our fingers around the direction it's moving. So in order to curl our fingers around that, we need to go like this with the right hand. It's called the right-hand rule, so you have to use your right hand for it to work properly. So you curl your fingers around that, and then the direction your thumb points, which in this case is out of the page, this way, is the direction of that angular velocity. Likewise, if you were going clockwise, now in order to curl my fingers that way, I have to turn my hand, rotate my hand the other direction, curl my fingers. Now my thumb would point into the page, down that way, so the angular velocity would be into the page. Just wanted to introduce that quickly. It'll be the right-hand rule will be more important when we get to talking about torque, but yeah, just wanted you to know. Just a quick reminder: circle is an angular displacement of 2 pi. One full circle is 2 pi, and then of course the linear distance is the circumference, which is 2 pi r. Oh, and in order to get from if you recall from the arc length formula, this angle had to be in radian. So in order to translate from rotational to linear variables, we need to be in radian. For these equations, it doesn't really matter as long as if you're using degrees, then you need to use degrees per second for your velocity, and all time is time. Yep. So, a student is spinning a stool with constant angular velocity when he notices two bugs sitting on top of it. Bug A is very close to the middle, while bug B is close to the edge. So we've got a stool. Here's the middle. Bug A. Bug B. Okay. Jim. Well, I guess Jim was the student at some point. It's probably Jim Lim. Spins the stool for some amount of time, and we want to see which is greater. Okay. Distance traveled by A, distance traveled by B. Let's think about it. Okay, so A is much closer to the center, so A is traveling along a circle like this, while B is traveling along a bigger circle, so distance traveled by B is going to be bigger. Angle covered, well, they're on the same stool, which means that they'll be rotating the same angular distance. Again, B is traveling a greater distance in the same amount of time, so the linear velocity of B is bigger. Angular velocity, well, the stool has a constant angular velocity. Both of them are going around at the same rate in terms of angle, so those two are equal. Angular acceleration, well, we have a constant angular velocity. That means our angular acceleration is 0. So the angular acceleration of each is equal. Tangential acceleration, again, is equal because if the angular acceleration is 0, the tangential acceleration is also going to be 0. If the rate at which the stool is spinning was speeding up or slowing down, then you get an inverse relationship where B's linear acceleration would be greater. And then centripetal acceleration, that's something that's related to angular motion as well. So we might need to stop and think for a little bit. But if we recall, centripetal acceleration we could write as 4 pi squared r over period squared. So the period is going to be the same for both of these because they take the same amount of time to make a circle. So then the centripetal acceleration is directly proportional to r, and therefore centripetal acceleration of B is larger. A disk begins from rest with constant angular acceleration. After time t, it's rotated through angle theta. What angle has it rotated through after time 2t? Well, begins from rest, constant angular acceleration, time t, angle theta. That sounds like the time-dependent equation to me. And since we know it begins from rest, omega naught is 0. And we have the constant angular acceleration. So we can see that the angular displacement proportional to t squared. So 2t means we get 4 times the angular displacement. The ball rotating at angular speed omega, you can see accelerating at a constant rate, rotates through angle theta before coming to a stop. Another decelerates at the same rate, but covers angle 2 theta. What was its initial angular speed? We've got all the variables there to use the time-independent equation. They both come to rest, so that's 0. And what are we were changing the angle. We want to know the difference between initial angular speed. So looking at that, delta theta, omega naught squared. So omega naught is proportional to square root of our angular displacement. So if we go to 2 theta, then we get a factor of root 2 on our angular speed. Cylinder begins rotating from rest with angular acceleration alpha for t seconds, covering angular displacement theta. Another cylinder begins rotating from rest with angular acceleration 2 theta. How long does it take to rotate through angle theta? Well, this is another one coming from rest, time independent. Okay, and we want to know relationship between time, what happens to time as we change alpha. So if we do a little bit of algebra, we get this. So square root, so we can see that time is proportional to 1 over square root of alpha. So 2 alpha means we get 1 over root 2 times c. Athlete wants to spin a basketball on his finger. In order to do so, he gives the ball an angular velocity in the clockwise direction. Then friction with his finger decreases the ball's angular velocity. In what direction is the angular acceleration of the ball? Well, it's going clockwise, slowing down. And slowing down. So that means that our angular acceleration is in the opposite direction of angular velocity, which is therefore counterclockwise. Or, so if the ball is spinning clockwise, right-hand rule, that would I curl my fingers that way. My thumb is pointing down into the page. So omega is down, which means our angular acceleration, alpha, is up. A CD moves with constant angular velocity. Is the point on the edge of the disk accelerating? That's a good question. Let's see. So, it's point on the edge of the disk accelerating. Well, constant angular velocity means angular acceleration is 0, which means tangential acceleration is 0. However, a point in the CD is moving in a circle. And anytime we're moving in a circle, that means that centripetal acceleration is not 0. And therefore, the point is indeed accelerating. Because the relationships amongst our angular or rotational kinematic variables are the same as the relationships among our linear variables, we can also do graphical and graphical and calculus relationships, just like we did with our other variables. So angular displacement from t equals 0 to 10. Well, on a velocity time graph, angular displacement is area. So got to find this area, this area. Displacement means the area under the curve is negative, area above the curve is positive. Because this is a straight line, we know that this has to be 4 2/3. You can do the math yourself if you want to. So this is a trapezoid, 1/2. Height is 60. Base 1 is 4 2/3. Base 2 is 2. So then what do we have? We have 30 times 6 2/3. That's not fun. But it works out nicely. So that's an area of 200. We go down here from 4 2/3 to 10. 1/2 height is 40. Base 1 is 2. Base 2 is, see, from 4 2/3 to 10 would be 5 1/3. So that's 20 times 5 1/3, which is 106 2/3. So then the total area, what's above is positive, what's below is negative. So the angular displacement is about 93.3 radians.